Okay, so what we're going to talk about now is an introductory class. For some reason, when I was an undergraduate, I majored in math, and it seemed like every course I ever took, the first lecture was on set theory. It's like every course. I had this lecture like many times. But anyway, just, you probably know what a set is, but we'll cover this topic anyway. A set is usually represented as like a capital letter, and then is equal to, we could say, yeah, we could say really anything, like let's say the vowels. So that's a subset of the letters of the alphabet, and in this case, all the letters in the alphabet are the entire alphabet, and then this would be a subset of them. So this is an example of a finite set. We could also represent an infinite set by doing something like this. We could say B is equal to all x's such that x is integer, and sometimes a semicolon means n, like I'm going to make a list of conditions. X is greater than 0, and maybe another condition. X is odd. So any value that meets all three conditions would count. So the set B would end up being, another way we could have written it was like this: 1, 3, 5, ... hoping the person can see the pattern. So this is an example of an infinite set. There's infinitely many members of the set, and it's not every integer. It's some integers, the ones that are greater than 0 and odd. So 3.5 doesn't count because that's not an integer, even though it could be argued that it's odd. And so a set could be finite or infinite. Then we'll have the concept of, and this is kind of some set notation, we'll be able to say things like, let me erase these examples. Let me put up simpler examples, and then I'll use some of this notation. So suppose we had a set A equals 1, 3, and 5. And we have another set B which equals 1, 2, and 3. Those are both finite sets. And then suppose we had operations, and this will come up in your computer science career. This will come up in database systems where maybe this is a table and this is a table, and you're trying to find entries that appear in both tables, or maybe appear in either table. So we could say, like for example, we could say, we could ask the question, is A superset of, is everything that is contained in A also contained in B? And in this case, the answer would be no. No. And even if it went this way, the answer would be no. Because, so this symbol means a subset of.
A is subset of B.
Right, is A a subset of B? And so what we're saying is A 1, 3, and 5, is every member of this set, does that appear here? And if not, then it's not a subset. So here we're in a situation where I'm going to draw what's called a Venn diagram. We have a set A, we have a set B, and where do they overlap? Maybe I should make this.
1 and 3.
So 1 and 3 is where they overlap, right? Let me make the overlap a little bigger. So 1 and 3 appear in the overlap. B also has 2, and A has a 5. So from our point of view of where they overlap and not, the picture kind of looks something like this. This would be set A, and this would be set B. And this is actually, this kind of football-shaped thing is where A and B overlap. So, for example, we can use as other operators we could use is we could say this. A, the intersection, so this is going to mean like the union of those two, of A and B equals the set 1 and 3 equals this set. This area is the, maybe we should even write that in. This is A union B. No, sorry.
No, intersection.
Intersection, sorry. What am I doing? Getting this thing wrong. Okay. The intersection of, so you remember this from a while ago. This would be, sorry, this would be 1,
2, 3, 5.
2, 3, and 5. Okay. A's intersection with B, that would be only elements that appear in both A and B.
That's 1 and 3.
Would be
1
and 3. Okay. So, and it kind of, it's easy to follow if it's done pictorially. But I'll have let's just have a formal definition of those, what unions are. Unions and intersections. So, a union, the set A union B is the set X such that the member X is either in A or in B. So we could kind of write that out in words. We could say X is, we'll use this symbol to mean contained in, a member of. X is in A or X is in B. So that's just kind of like in set notation what it means, but it's usually better to see that as a picture. The intersection of A and B would be any member X such that it meets the following condition. X is in A and it has to be in B. It has to be in B also, so it becomes an and. X is contained in B. And then it's in that intersection. Another interesting set operation might be A minus B. And sometimes that looks a little confusing, so some books might call it A, kind of a backslash B. Have you seen it either way? Or, meaning everything that's in A but does not exist in B? So that would be X is, all X is such that X is in A and X is not in B. And let me just pictorially draw that. So here's A, here's B, and we're interested in this stuff. The stuff that is in A but not in B. And there's two different ways to write it. It's like that. So this might show up like in, let's say you're creating a website and you have a bunch of users. Maybe your business has two sides to it, and this is one set of customers, this is another set of customers. And maybe these represent customers who have done some kind of business with you in the last month. And you want to send an email out to like customers you haven't heard from in a month. So you just want all the names of the people who are here but have not done business with you in a month. So you might say, give me all the people in group A but are not in group B. Maybe group B is that they're here's a better example. Suppose these are customers who say they don't want to be contacted by you. They don't want junk mail from you. So you would say, give me all the customers who are in a group that hasn't made a purchase in the last month. These might be people who don't want any email from you. And then you want to build a list so you could send out an email like, welcome back or come shopping here again, or something like that. So you'll have to do an operation on your database that involves kind of set theory like that. Okay, so we have some examples of notation, and it's sometimes good to see the diagram and maybe go through an example. So suppose we have, suppose we wanted to go through an example. Let's say we have, you're using Facebook, and so, yeah, we'll do an example. Friends on Facebook. So do you guys use Facebook?
Yeah.
Okay, so you have, yeah, the whole world does, right? Okay, so let's say we had three people on Facebook. So we'll use, your name, Deep? Okay, so let's say, use Bill, and let's say we'll use Chin. Three people on Facebook. So let's say Deepthi, T-H-I, has 65 friends. And let's say Bill has 45 friends. And Jen has 42 friends. Okay. Now Facebook will tell you, if you're logged in and you click on one of your friends, it'll tell you how many mutual friends you have, right? But it won't, you can't click on two friends and say, how many mutual friends do I have with these two people? It's always like you and one other person, right? So let's say B and D, right? I'll do like each combination of two people have 20 mutual friends. Mutual. How do you spell mutual? Yeah. Mutual friends. Okay. So that would be this combination. Then let's say D and C have 25 mutual friends, and B and C have 15 mutual friends. Okay. So now the question is, you want to know how many mutual friends do all three of these people have? Now, I don't know if there's a way to get this out of Facebook, but let's say the total friends of all three of us is 100. If you took all your friends and my friends and Jen's friends and put them all together and removed all duplicates, it would come to 100. So is there a way that we could figure out, using this data, how many friends that are mutual between all three of us? And in a case like this, so if you had access to the database, like Facebook has a database of who's friends with who, they must have some friends table that says, you know, your ID is friends with all 65 people. So they must have a table somewhere that says, like, person A is friends with person B, and just lists, well, every time you had a friend, you get a new entry into that table. But if we wanted to figure out how many people are friends of all three of us, can we figure that out? And you probably, if you want to solve this, you'd be using set theory. You might not think you are, but you'd be going something like this. You have all of one person's friends, and just whenever you have sets, you always want to make them interloop with each other, being mindful of the fact that where they loop could be an empty set. It's possible. So then we have a second person and we have a third person. So let's say we have D and B and C. Three different people. And what we're trying to figure out is how many people are here. How many people are friends of all three of us? So we know how many are in D. The set D has 65, the set B has 45, and the set C is 42. We also know how many people are friends of both B and D. Right, we know that. We know how, so we know how many people are in here, we know how many people are in here, and we know how many people are in the three footballs between the two. But we're trying to get this one in the middle. So any way you can think of getting that? So we know that the total of all of these is 100. All three circles combined we know is 100. So we can set up an equation. 100 equals, suppose we just said, I'm going to use the symbol, the number sign, the number of members of B, plus the number of members of B,
plus number of members in C.
plus the number of members of C. Is that right?
No, minus, we need to minus something.
Right, and the reason this is not right is because we've counted all the people. Let me color these. Color that one green. This one. And should I put the marker? I think I have another one. This is a brown marker. I hope it shows up as a different color. So this equation counted this area, all the people in this area once, all the people here once, all the people here once, which is good. But we counted all the people in green twice.
Yeah.
All the people in brown twice, all the people in blue twice, and how many times did we count?
3.
3 times. So if we subtracted all the overcounts, if we said minus the number of people in D union B,
Yeah.
D union B,
Minus D union C.
yeah, minus,
D union C.
minus the number of people in,
D union C.
yeah, D union C, minus
DB union C.
the number of people in,
B union C.
yeah, let me do it here. The number of people in
B union C.
B union C.
Plus.
Okay, now that, we're still, is it 100% right yet?
No.
No, because now what we've done is, we've counted everyone here, we've counted this twice, but then subtracted it once. We counted this twice, subtracted it once, counted this twice, subtracted it once. So originally we added this in 3 times, now we have subtracted it 3 times. So this piece has not been added in.
Yeah, so we need to add once.
But that's the number we don't know. So if we said, well, yeah, so it should be, we should add it, we should add it back. The union of, I'm sorry, the number of people in D union C union B. If we edit that back in, but that's the number we don't know. But we know all these other numbers, so we now have an equation. So 100 equals 65 plus 45 plus 42 minus 20 minus 25 minus 15 equals the thing we're trying to figure out, and then we can, it eventually comes out, the answer was, I think the answer comes out to 8. So the number of people in D union C union B is 8. That ends up coming out the answer. So we would be solving this question using set theory. Obviously, however we want to solve the problem was, we're taking, these are the pieces of information we can get from Facebook. You could log in, you know how many friends you have. You can pick any individual person and see how many friends you have in common with that person, but there's no operation on Facebook that does all of them. So, so if we wanted to calculate them, we would use set theory. And then, you know, okay, so that, I'm just trying to like give maybe a little bit of a real world example of how set theory could come into play. Let me do another example. And this kind of shows up, I don't know if you've ever been interested in thinking about going to law school, but they have a LSAT test, a test you have to take to see if you have an aptitude for law. And there's a logic test, and a lot of the logic test is set theory. So suppose we had a couple of facts. Fact 1 is everything in your garage is useful. So everything you put in your garage is useful, okay? And then your fishing poles, fact 2, your fishing poles are useless because they have no hooks. And then okay, and then you're asked to draw a conclusion, and this is hopefully a simple example, but a conclusion. Suppose you want to draw a conclusion. Everything in your garage has hooks. So, I mean, it's kind of a, hopefully this is a silly example, but it's kind of a, if you take a couple of facts, can you then draw a new conclusion on those facts? And it's all going to, well, what would your argument be? You'd be using set theory, but you might not know. Would you say this is a true statement? And what would be your, if it's true? So basically, you're saying everything that you keep in your garage is useful. Anything that's useful to you, like a bicycle or a spare tire for your car, you put stuff that's useful. You don't. So in other words, you're not a person who saves junk. Let's say junk is stuff that's useless. It turns out you own some fishing poles, and they're useless because they have no hooks on them. So and then from those two facts, we could make many conclusions. So. Suppose someone wanted to make the conclusion, everything in your garage has hooks. How, would you say that's true or not true, and how would you argue? Usually, if something is true, you have to show that everything you own meets the condition. If you say it's not true, all you have to do is show one case where it's not true. So.
Yeah, I say no because the conclusion is not true because we can't say everything whatever we put in the garage is only a fishing pole. It can be any other.
Right. Right. It could be things that are not a fishing pole.
Yeah.
So in the end, it kind of comes down to a set theory. Or maybe we could draw those. We could draw a diagram of sets, but it might look something like this. This is the stuff that's in your garage. This is the set of stuff in your garage.
And that,
now, is everything in the garage useful? Oh, everything.
Yeah.
Okay. So actually, the set of everything that's useful is this set. So this is all useful. Now, are there things? Is it possible for things to be useful and not in the garage? Yeah. Yes, because what we're effectively saying in the first statement is, of all useful things, the ones that are everything in the garage is useful. There may be things useful that are outside the garage. Right? So the useful stuff is here. And everything in the garage is useful. So everything in the garage is a subset of the things that are useful. The fishing poles are useless because they have no hooks. So we can almost think of it as like useful. The useful's complement is useless. All things that are not in this circle are considered useless. And now where would we put the set of fishing poles? Do they overlap? Are some useful and some useless? Or according to this statement, they're all useless because they have no hooks. So the fishing poles would be out here. So this box represents all your stuff. This circle represents all the stuff that's useful. Everything in the garage is useful, so everything in the garage is a subset. Maybe everything useful is in the garage, but it's either equal to this useful stuff or a subset of it. And now we're being asked a conclusion. Everything in the garage has hooks. So the question is it possible that something could be here or here that has hooks. And that's possible. So all we'd have, everything in the garage has hooks. So the way we would prove this conclusion is wrong is to think of it, show that it's possible that something could be here with hooks. So what, besides fishing poles, what has hooks? Can't really think of anything right now. But if there was something that had a hook, whether it's useless or useful, it could be outside the garage.
Yeah.
So that's not a great conclusion. If we ask, but this is the way our sets are set up. So everything in the garage is a subset of everything that's useful, and the fishing poles are a set that is in the complement of useful stuff, on the useless side. So is there anything we could also ask about this, about these sets? So for example, if we ask the question, is it possible that there is something useful that's not in the garage, the answer would be yes, that would be something out here. Is it possible that something could be useless outside of this circle but be in this circle? And that's not possible. That's not possible because of the statement, everything in the garage is useful. Okay, so I'll do another example. Let me do a similar example now. Suppose we have the following facts. Here's the green marker. Okay, poets are happy people. And when we say that, we're assuming it means all poets. Okay. And let's say fact 2. Every, let me make this every. So every poet is happy. Every programmer is wealthy. Okay? So whoever's coming to these conclusions, we're not going to challenge why they've come to this. And fact 3. No one is happy and wealthy. Okay, so suppose all 3 of these are true. Wait, sorry. No one who is happy is also wealthy. Okay. So if these 3 statements are true, what do our sets look like? Or I guess the question is are these legitimate conclusions? So let's try a first conclusion. No poet is wealthy. Is that a conclusion we can draw? Is that a conclusion we can draw from these facts? So let's see, let's draw, so basically, again, these are statements about the general population. So we have a universal set of all people, and that's all, that represents all the people. Poets are happy. So how do we represent that in sets? I should say poets with an S.
Happy. Poet is.
So we have a set of happy people.
And
So we can draw a circle.
happy is subset of poet.
No, poet
Poet
is
is a subset of happy.
right, because every poet is happy. So
Every
this
poet
is,
should be inside of happy.
this is happy. Poets are on the inside. Okay, every programmer is wealthy. Now, wealthy could intersect with happy. They could overlap, unless we can see a reason they can't overlap. Every programmer is wealthy. Okay, no one who is happy is also wealthy. So in this happy thing, there's no wealthy people. So happy and wealthy are disjoint sets. They have no members in common. So wealthy would be over here. And every programmer is wealthy puts programmers in this set. That's a subset of wealthy, and happy and wealthy are separate. So the question is, the statement, no poet is wealthy, ends up with these three facts. I'm not saying these are actually true. If these three were true, this would then be true. And it, again, it comes down to the set theory. So let's see, what would be another conclusion we could ask? Programmers are happy people. No, that wouldn't be true. If we had made this, are these people in the set happy? Actually, none of them are. And then the question, nobody could be a poet and a programmer. Can a person be a programmer and a poet? A person is a poet and a programmer. Is that possible? And the answer is no, because the set happy people and wealthy people are disjoint sets. And poets are in the happy and programmers are in the wealthy, according to these statements. Okay, now what if we were to change this to say some? So here's what I'm basically doing is going over an example where we're taking sentences out of just the English language, and based on whether we say every or some, it's going to change our picture. And in the end, we're going to use set theory to see if these conclusions make sense. But if we said some programmers are wealthy, what would that do to our picture? Some programmers are wealthy would put, where would programmers show up? If every poet is happy, we still have this, poets inside of happy. No person who is happy is also wealthy makes the wealthy section completely disjoint from the happy section. And now I'm saying some programmers are wealthy. Where do we draw programmers? So that's implying some are wealthy and some are not wealthy. So now the question is, where do we draw them? Well, some of them is going to be an overlap. Some of them are going to be in here. We'll draw programmers in a different color. Some of them are going to be in the wealthy section, and some are not. Where do we have the freedom to go through? Can we go into the happy and the poets section? Is there anything making us not go there? We never said programmers are not.
No one who is happy is also.
Oh, no person
who is happy. No
So you
person
can't go into
is
happy.
also wealthy. But that's okay. So we can go right through happy, and we can even go right through poets.
No one who is happy is also wealthy. So the factory means that whoever is happy is not wealthy, right?
Right, but right, because of fact 3, we have to keep the wealthy circle and the happy circle separate.
So,
Poets are a subset.
okay.
So basically, what we're talking about is like the operations we've talked about before. A subset, one is a subset of another set.
So we
They
are-
overlap or they're disjoint. Is coming. We're going to have to try to read it out of English and then draw this in our
Okay,
head.
now we are sorting out for fact 2, right? Some programmer is wealthy, so we can.
Right. So some are in this circle and some are outside the circle. Now, how far can we? What are the
Yeah.
of all the other sets, we want to try to cut through as many as we can unless there's some fact that tells us we can't. So we'll have the whole picture of all the possible things that can happen. So some are wealthy, some are not. Now the ones that are not, can they be happy? There's no rule telling us they can't be happy. And there's no rule saying if you're a poet you can't be a programmer. So the programmers can go like this.
Yeah.
So these are now our programmers. So now, so just by changing this from every to some, all of a sudden, it is possible to be a programmer and a poet. And you will be happy. So even kind of like a kind of an interesting question would be, which someone might not see right away, but once you draw the picture, is a conclusion. Can a person be a programmer a poet, and 3, happy? And the answer is yes. That would be a person here. If we said, can a person be a programmer and a poet and unhappy, meaning you're in the complement of happy, so anything that's outside of happy would be unhappy. The answer to that would be no. Because if you are in the collection of people who are poets and programmers, you have to be happy, based on these rules. So basically what I'm trying to do is I'm trying to say a certain set of facts. You could be investigating a criminal case or whatever. You have a certain set of facts. A lot of times the facts, whether the word every or some appears in the facts, might determine whether you have to be inside of a circle or partially inside, part is outside, depending on the words. And you end up drawing a picture like this in your mind and then asking yourself, is it possible to be here? Is it possible to be here? Is it, all the different places where you could be. So that is a logic thing that goes on with people who are in law school, preparing for law school. They give you a couple of facts and then they ask you questions. Is the following conclusions possible or not possible? And the best way to solve that is to draw the picture and then just ask yourself, is there an area where that comes, where it can be true or not true? And then the last topic I want to talk about is induction, mathematical induction. So suppose, for example, and maybe I'll do this, I'll give an example. Suppose somebody wanted to make this statement, so I'll call this induction. I'll call it proof by induction. Okay, so suppose somebody observed a pattern but wasn't sure if it was always true. Let's say, for example, somebody wanted to say that the first n odd numbers sum to the first n odd numbers sum to
do they sum to? So for example, 1 plus 3 plus 5 sums to 9. 1 plus 3 plus 5 plus 7 sums to 16. So if you take the first starting at 1, 1, and then just keep adding all the odd numbers together, they're going to sum up to something. Suppose somebody wanted to make the statement, the first n odd numbers sums to n squared. Right? The first 3 odd numbers sums to 9, which happens to be 3 squared. The first 4 odd numbers sums to 16, which happens to be 4 squared. If we said 1 plus 3 plus 5 plus 7 plus 9, that would sum to 25. And since there's 5 numbers, that again is true. Now suppose you ask yourself, is this going to be true forever? Can you make an argument? It seems like it's a pattern that's working so far for low numbers, but will it work forever? Does it? I was hoping that's an example that it doesn't, maybe you might not see a pattern, but does it seem like it will always be true?
Yeah.
But yeah? Well, is there, okay, so one argument you could make is, yeah, I guess you just have to show this is always true. So this is a proof not by induction. There's, the number of numbers is going to be, like in the case with 3, there's 3 numbers. So it's going to be 3 times, now these are all different numbers, but maybe what is the average of these numbers? A 1, a 3, and a 5 are going to average to 3, the middle number. Right? So if there's an odd number of numbers, like if we had 1 plus 3 plus 5 plus 7 plus 9, we have 5 numbers. Now if we said, well, why don't we take 5 times the average of all these, that would be, it would be like adding all these up. Multiplying them by their average would be the same as adding them all up. And their average is going to be, like the 9 and the 1 are going to average to 10. 9 plus 1 is 10, divided by 2 is 10. 7 plus 3 is 10, divided by 2 is 10. So the 7 and 3 average to 5. The 9 and the 1 average to 5. The 5 averages to 5. Everything averages to 5. So it kind of looks like 5 numbers times their average would be 25. So 5 times 5. And if it was an even number, it would be 4 numbers times their average. And the 1 and the 7 average to 4. 1 plus 7 is 8, divided by 2 is 4. The 5 and the 3 average to 4. So you can kind of see this pattern. But suppose you didn't see that pattern, but you wanted to prove that it's always true. Well, you could make the observation, if somebody said the statement, it would be 1 plus 3 plus, and we'd go on and we'd eventually, the last number will be whatever n is times 2. 2n minus 1. Right? So if it was 1, 3, and 5, that would be 3 numbers. The last number is going to be 3 times 2 was 6 minus 1, which would be 5. Right? So if you wanted to say, what are the first 10 odd numbers? It would be 1 plus 3 plus 5 plus 7 plus 9. We go all the way up until we got to 20 minus 1, until we got to 19. Right, so that would be the first 10 odd numbers would be 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, and we'd stop at 19. So however many numbers there are, we'd take 2 times that minus 1. So the claim is that this will equal n squared. Someone is saying that this is always true, and we see it works for small numbers, but will it go, as we go out to infinity, will it remain true? The way we can prove it is, we could use proof by induction, where you say if it's true for 1, and if P, the property, if P of n P of n minus 1 is true, then P of n is true. If you can show that this pattern says, if first of all, if we can show it's true for the number 1, and then show if it's true for any number, it's also true for the very next number, and that's true for all numbers, then we've actually showed it's true for all of them. So, and this is called doing a proof by induction. So, if we said, so first of all we ask ourselves, is it true for 1? Is the statement 1 equals 1 squared? Is that a true statement? And the answer to that is true. Now the question is, if it's true for any number, will it always be true for the very next number? We're not trying to prove them all in one shot. We're just saying if it's true for the 3rd number, it's also true for the 4th number. And if it's true for the 9th number, then it's also true for the 10th number. If we could show that there's a pattern that if it's true for any number, it's always true for the very next number. And if it's true for the first one, we've really shown it's true for all numbers. So, the question is, can we show that it's true, let me just make some room here. Can we show that if it's true for one number, it's true for the very next number? So if we took this and then just added the next number, what would that be? Okay, the very next number would be 1 plus 3 plus dot 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 plus 2n minus 1. What's the very next number? 2n plus 1. That's the one after. And then if we add this to the number, then we also have to say this should be equal to plus 2n plus 1. So if we just add, so let me do an example of that. Suppose we had n equals 3. Well then 1 plus 3 plus 5 equals 3 squared. Now we're saying if this is true for 3, what about the case for 4, when n equals 4? Then it'll be 1 plus 3 plus 5 plus 7 equals 3 squared plus 7. I'm just doing it. That's all we're doing. We're just saying let's add the very next number to both sides and see if it's still true. So I took all the numbers up to n minus 1 and then just said let's add the next number here and then take the previous answer and add 2n plus 1 here. So now we can say that, what is another way of writing this?
n plus 1 to n plus 2. N plus 1 whole square.
N plus 1 squared. Right, so you're right. Another way of writing this thing, right? N squared plus 2n plus 1 could also be written as n plus 1 times n plus 1, n plus 1, which is n plus 1 squared. So it looks like if we used any number n, and said, well, let's consider, if we took this original statement, all these numbers equals n squared, if we said, well, what would happen if we added just the next number to both sides, what would happen? We would get the new pattern is equal to n plus 1 squared, and then it shows it's true for every number. If it's true for 52, it's true for 53. And if it's true for 112, it's true for 113. So as long as it becomes true for one thing, the case where n equals 1, if that's true, well then it's true for 2, and therefore it's true for 3, therefore it's true for 4, and that can go on forever. That, I don't know if that sounds, looks like it makes sense. And where this shows up in computer science is when, have you taken an algorithms class, computer algorithms?
Yeah,
Okay.
algorithm design, yeah.
So did they get to a point where you give an algorithm for a program and you have to prove it will work for every input?
Yeah.
Because, so basically what happens is you have a question, you write an algorithm that solves that question, and you can run it on a couple of inputs and go, oh, it looks like it works for a couple of inputs, but you want to know, will it work for every input? And a lot of times when you're doing the proof of correctness of the algorithm,
you want to somehow order your inputs to say, well, if it works for this input, it should work for the very next one, and therefore it should work for all inputs. So is it gonna end up being proof by induction is the most common way to prove the correctness of an algorithm.